Good afternoon, everybody. My name is Ramon Mata-Toledo, and my co-author, Jose Mujica, who is actually the driving force behind this paper, is with me here, although hopefully his system will not fail as we have experienced before. So let me go back in here and start the show. Today we'll be talking about using a underdamped differential equation and the graph that is generated to explain the response of a loudspeaker. Before I start, let me give you a little bit of background. Most of our students are sound technicians. So we are always been looking for examples or application of differential equation to something that catch their interest. By experience, we have seen that math needs to be a closed work. Not everybody seems to like it. And generally, not only the way it is taught, but the content. So we have always been concerned, how can we improve and make the math classes a little bit interesting? And I have found that, for instance, some of my students tell me that they don't like math at all. Okay, so we probably have heard that many times. But something that concerns me here is how we can improve that. Now, I have never heard anybody, I have never heard a woman, for instance, saying that she is the ugliest woman in the world. I have never seen a guy saying, I'm the dumbest guy in the world. But I've seen quite often people saying, I am the stupidest people when it comes to mathematics. I'm the worst mathematician you can ever have. And they say that with pride. So it's something that we are proud of, and I find that very intriguing. So Jose and I have always been trying to find examples that can motivate students and make mathematics very interesting. So that's why we chose this topic. And we have also found that if you try to use graph, there are some advantages to doing so, and I would like to mention some of the ones that we have found. We have found that when we use a graph, the explanation seems to be clear. We seem to understand it a little better. It also allows to convey the essence of our work and make it more understandable. Not only when we write about it, but we also when we explain it. And it also serves, the graph serves as a shortcut to avoid talking about separate but similar issues with the phenomena that we may be exploring. What happened with this? How do we, if we change this, what happens? How do what will we see if these variable is changed, whether it's increased or decreased? So we think that the graph allows us to explain some of those in a simple way, and the students seem to understand it. We chose for this particular type of student to study the response of a microphone. And the reason that we chose the underdamped is the equation, the underdamped equation, is the closest to the phenomenon that we are trying to study. And the reason that I say the closest to Acustica. But for instance, when we're going to study the sensitivity pattern of a microphone, what we generally do is we measure the output of the microphone from different angles. In this case, we are seeing it as part of a polar coordinates, and that's the way we graph, but we measure try to measure the different angles. The result of that, the result of this measure, and when we plot it, it's going to be a cardioid. Now, the, 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 the approach that we always take is we take a graph generated by the computer and we try to approximate it to the real graph. That way, we can manipulate inside the system the different parameters, and until we get the result we want, or we think that it's decent result to obtain. And we use that tool, that graph that we are manipulating, as the tool that allows to answer some of the questions of the student. So notice here at the left, we have a cardioid that is generated by a formula, mathematical formula. All these graphs we have been generated using Mata. So this graph in here, okay, notice is the one that is generated by the computer, the one at the left. The one at the right is the one we get by the manufacturer. The manufacturer offer them, it says this is the sensitivity of the microphone. This is what we obtain in our labs. And obviously they have some time more embedded equipment that we are, so the measurement may be more precise. But here is where we see that there are similarities. So how do we tweak the one at the left to obtain results that are closest to the one at the right? And that's one of the things that we are trying to do. We are not trying to reinvent the wheel here, but how can we use what we already have to approximate what we want to study? And this is the approach that we have taken. The paper per se, the presentation per se, I don't think we get us to 25 minutes because there are steps that we omitted. For instance, the solution of the different equations have been omitted. The reason for that is that we are preaching to the client. We don't need to tell you how to solve an open differential equation, but we will present some of the arguments. So if you have any questions, you don't have to wait for me to get to the Q&A section. You can just interrupt me and ask many questions. So I would like this to be as interactive as possible. And if you think you have something to contribute, by all means do so. This is not here just to dazzle anybody, just to talk to friends about mathematics. So here we're gonna show you again, okay, the graph of a reverberation time of a closed water room. So again, we have the actual graph of the real graph, and we have the one at the left, that is the computer one. We can see here that they are somewhat similar. They are not identical, but we can see, we expect that if we manipulate the thickness, twinkle a little bit with the parameter of the formula at the left to allow us to generate also the formula. So that's what approach. Our approach always is, let's take something that we have, and let's look for a curve that looks very much what we already know, and then if we can approach the real thing by using the computer. So these two graphs, as you can see, are very similar, but not identical. Okay, so how do we go about it? Well, the first thing we do is we can manipulate the parameter. And we keep playing that until we get something close to what we have. We may not get an exact, but we wanted to get it as close. Now we have said that. The reason that we chose an underdamped differential equation for the phenomenon that we have is because of the one that we said is the now, we started with the general form of a circle for the homogeneous differential equation. And we present it here, as you can see. And again, I don't need to show you how to resolve that, except that for a student, we do that step by step. So when we do that, we generally give them, like, this function below work as a solution to that equation. We show them all the process. At the end, we make the necessary trigonometric transformation to make the simplified expression until we get a solution that we want, the solution that we are looking for, and that we are going to plot. In this case, use matrix. The school that where these classes are taught is not as fancy as in school. There are some technical limitations. Sometimes we try to do with whatever. By the way, in case you want to know what that school is, it's in Caracas, in Venezuela. So you are listening to the news, you know what some of them difficult facing. So with the equipment that we have, we try to do the best we can. And in particular for the students who are interested to be sound technician. That's what the school is using, sound technician. By the way, they take mathematics. They take 4 mathematics, 4 calculus, including differential equations. That's 3. So that's where we try to use this example. So because that's the field that we are operating on. So engagement in something that we like. Well, now that we know what the general form second homogeneous second order homogeneous differential equation is, and we show them step by step how to get to the solution, we would like them to use our equation for an underdamped system. The underdamped system that we are using here is a loudspeaker. When we apply that solution, general solution, to the underdamped system, we're going to obtain, as I said before, we're going to apply this speaker. Here you can see the simplified view of what it's allowed to speak. As we all know, the speakers, this zone in here that you can, that we have in purple, generally it's shown in black in here. The speaker, you can see that vibrate not sideways, but in a single direction. You move back and forth. Okay? And that's what we have. We have one degree of freedom. But to obtain that degree of freedom, there are some mechanisms around it that not only facilitate keeping in place and allows that movement back and forth. So we see it as vibration, but if we look at it, it's moving back and forth. It's not vibration, it's just moving back and forth. And that's what we try and visualize here. These phenomena that we're trying to manipulate. So let me show you in here. When we plot this equation, notice the equation that we obtain. We can observe that the curve reaches a maximum. And when that maximum, actually that is a maximum, goes down to a minimum, and then it's more or less waves around it. Now, this equation here that we have is somewhat compressed. So if you could expand it, you can see that it looks very similar to the one equation that I showed you before. Now, having said that, we try to represent that same equation in, in using a cellular revolution. This cellular revolution also generated by and show that when we look at it at the beginning, they don't seem to be very similar. If you look at this here and we look at this here, the same presentation, they don't look similar at the beginning. Both. If we look at here in this section that I'm showing, we obtain the same value as we have before. The same maximum is the same, minimum is the same. So that range of value here they are basically there are some small variations with the precision, but other than we can neglect those and basically the same. Now, if we represent that as an spectrum, the same formula, did it in three-dimensional, did it as a cellular revolution. Now we have an spectrum. You may think, well, where are the similarities? Well, look at this section here. Look at this section here. That section that you see here is the same section, has the same shape that you see here. Unfortunately, I cannot amplify this. The shape is the same. And remember, what we are trying to do is visualize these in 2-dimensional now, in 3-dimensional, and later. So you can see that the equation, you're seeing 3 different views of the same phenomenon. I think represent. One thing that is interesting here, we could say, is that one of these curves here is the same value that we see in the 2D, we see in the 3D, and we see in the So there are similarities there, but we need to make sure that we are looking at the same value. If we try to say that we get the same value, even though sometimes it's hard to see, because I cannot amplify this. Take by one for this graph in here, okay, it's a real 3D spectrum. And by the way, the graph is not showing but there should be a reddish section in this center that also has a similar shape. For some reason, it's not showing in the graph. Trying to see why it's not showing, but in this particular presentation, it's not. So that was a technical issue. But again, what we are trying to do, remember, is using the underdamped equation, the graph. Now that we have graphing, we try to see it in different degrees, the spectrum, and we find that the values are set. And here we have the sound pressure level. Here in the middle, we should see the shape that is also very similar to that. Now, here is something that we found. We are using a line radio spectrum. This is for low frequency, by the way. And there's something that phenomenon that is observed when we deal with high and mid frequencies and when we deal with low frequencies. The direction delivery for some is basically like an arrow, like we showed here. Okay. That is 125 hertz. So here are in the first quadrant, notice we have spectrum for 125 hertz. You can see here we have these representations. Now, if we were using a traditional speaker, we will not see these as an arrow. It would look more like a low. However, the newer technology, the line array speaker allows uh, to have a directionality that is basically straight as we have it. Now, if we go to low frequencies or some other frequencies sometimes, and depending upon the type of the speaker that we use, we see that the ability is not doesn't mean not straight. Instead, it tends to sparse, to be like a fan. It's open and basically going in every direction. So here we have a new unidirectional as opposed to omnidirectional. Basically, there's a fan open like a fan. But the newest technology allows us to see this phenomenon as we expect it to be in what's mid and high. One thing that we would like to show you here that notice that we can see that even for 125 hertz, these values will not show in traditional. One of the things that we would like is to apply this concept using the graph system in this particular development to other physical phenomena. One of the things that we found that we can apply to is the trampoline. What is that the responsible trampoline here is that if you take the response, notice that the curve looks very similar to what we have. So this is another phenomenon. And notice one is sound, one is the jump of the trampoline. Where else can we do this? Well, we found that we could also have this approach and obtain similar results when we use regarding. There's some of the rationality of the water. We also have the change, the opening, the closing of the mouse of the darting hole. And when you graph that, you obtain also, notice, very similar graph to what we have. So we believe that we can see here that we can apply that to explore some phenomena that may not be related, at least at first sight, but underneath they have very commonality that we can discover. I don't know if any one of you listeners have similar experience. If you have it, I would like to hear it. I don't know if you use this type of approach, but in any case, hear us out. As I said before, a presentation is not going to last 25 minutes because a lot of the details that we have was on how to solve this problem. We decided that we don't need to reach to the client. That we should make progress. So if you have any question or you have any comment, I would like to hear them. Please look up before. I was saying love. Share any. Or should I go through the list and say, oh, Tim Clayton, Cesar Martinez, or Bosha, or one by one? What do you say? Samuel, do you have any questions? and Bob Shan, if you have any questions. Tim Clayton, Cesar. Okay, does anybody have anything to say? Or Samuel, do you have any questions? No, I cannot see Bob Shan, but I can see Cesar Martinez. Press. So if any one of you have questions, please. Okay, so if you don't have any questions, then I will stop the sharing and let the other presenter continue. So then, thank you for being here. Thank you for listening to us, and hopefully this presentation will stimulate some of you. Let us know what you think. How we can improve. We appreciate it. Thanks. So I'll stop sharing.